Okay, so good evening, my students. And again, this is take 2 on the lecture on equilibrium concentrations and Kc. Okay, so like I mentioned in my other 2 videos, I had to re-upload. My first one did not have sound, unfortunately. So here we go for the second time. I will try to be just as thorough as I was in the first one. So let's go ahead and get straight to it. So this PowerPoint just covers some of the basics of equilibrium. It does not go into too much detail, which is why I kind of like it as a good intro PowerPoint. That way I don't overwhelm my students with too much information right away. Okay? So after today, after this lecture, you should be able to calculate the equilibrium constants for various reactions and calculate the equilibrium concentration using an ICE table. Excuse me. Okay. All right. So, So recall from last week's intro video that the equilibrium of reversible reaction is reached when the rates of the forward and reverse reaction are equal. Okay, so I did see some students that might have gotten a little confused with this part, but we're not talking about the actual concentration values. We are talking about the rates, the change in molarity over unit time, which is usually seconds, the change in molarity per second. That is the rates. So the rates of your reactants being converted to products and the rates of your products being broken down back into your reactants. Those two are equal, which means there is no change in the concentration of reactants and products. So one thing I want you guys to understand is that, don't know how to spell apparently. The concentrations are fixed. That means they are constant, they are not changing. But fixed does not mean equal. So the concentrations of reactants and products do not need to be equal, but they do need to stay constant. So there is no net change between the concentration of reactants and products. Okay, so hopefully that helps you. Again, this is at equilibrium for a reversible reaction. Okay, so let us continue. So for this, you will be calculating what is known as your equilibrium constant, which is represented by the variable Kc. Okay, capital K, equilibrium constant, little c stands for the concentration. So that means whenever we're using K lowercase c, we are using the concentration at equilibrium. Okay, so see, we are given this general reaction where you have A plus B yields C plus D, where the capital letters are your actual reactant chemicals, your substances, and your lowercase letters are the coefficients in front of your balanced chemical equation. So for the general reaction, again, once the reaction has reached equilibrium, the concentrations and the concentrations of reactants and products are related in the following manner. Okay, so you have your products on top, product C times product D, and recall that these brackets stand for the concentration, right? Those brackets mean concentration. So concentration of product D times concentration of product, or concentration of product C times concentration of product D raised to this exponent, which is your coefficient in your balanced chemical reaction. So that is divided by the same thing, but within your reactants. So, and that equals your equilibrium expression, equilibrium constant. So it is always your products over your reactants. Your exponent are the coefficients, not the subscripts. They are the coefficients of your balanced chemical equation, chemical reaction. The concentration, or the brackets, is your concentration at equilibrium. Okay, and that's why you're calculating your equilibrium constants. If the reaction is not at equilibrium, then you are not calculating your equilibrium constant. You're going to be calculating something else, and I'll be talking about that a little bit later. So just know, if you are calculating your Kc, the concentrations have to be at equilibrium. Okay, so let us go ahead and continue, my students. Okay, so this is where the conceptual stuff kind of comes in. So I would recommend paying close attention here. Okay, my highlighting skills not that great, but you understand that this is an important slide because this is the conceptual bit. This is something that you might see something more similar to this on your AP exam versus the calculations. So if you have a K value that is greater than 1, that means products are favored at equilibrium. So one way you can remember this, so you have K greater than 1, right? Think of this greater than sign as an arrow pointing you towards your products. Okay, and then if K is less than 1, the reactants are favored at equilibrium, and the same thing, K less than 1, think of this arrow as pointing you towards the opposite side, which is your reactants. So that might be an easier way to help you remember this as far as when you're looking at your equilibrium constant values, greater than, less than 1. If you look at the actual sign, it tells you the direction that is favored. Okay, so I would highly recommend studying this slide. Okay, so as previously discussed with Le Chatelier's principle, I probably butchered that. I'm not going to say I know how to pronounce it properly, but we've already talked about this without actually giving it a fancy name. So we talked about this whenever we're adding or removing chemical species from either reactants or products, and we're looking at the shift in the equilibrium. Okay, so according to this principle, we do not include pure solids or pure liquids when we are writing our equilibrium expression. So that means if you have any substance, say H2O, and it is a pure liquid, or it has an S next to it, pure solid, we do not put those in the equilibrium expression. Next, only equilibrium concentration can be used. I already mentioned that. And finally, concentrations are always in molarity. Okay, so let's go over an example. Excuse me. It says the equilibrium concentration for CO is 1.5 molar, and for CO2 is 0.81 molar. What is the concentration of the O2 given a K value of 15.3? Okay, so we are solving for an unknown concentration. We don't know what O2 is. So in order to solve this, my first step is to write my equilibrium expression. Okay, so to do that, it is your products over your reactants, and then we need to also include the coefficients. Okay, so my product is just CO2, right? This is my product. My reactants on this side air, I don't know what that noise was, are CO and O2. Okay, so let's go ahead and start writing. So my equilibrium expression Kc equal to my product, which is CO2 squared because the coefficient of 2, divided by CO also squared because the coefficient of 2 times O2. Okay, O2 doesn't have a coefficient, so it does not need to be raised to any specific power. Okay, so now let's fill this in with the actual values that I know. Okay, so CO2 is 0.81 molar. I hate how it zooms in whenever I put my hand down, but oh well. 0.81 molar squared. Okay, divided by, I have CO, oops. Okay, no, I'm sorry. CO is 1.5 molar, 1.5 molar squared times O2, and I don't know what O2 is, so I'm going to leave it as X, and all of that is equal to 15.3. Okay, my K value is 15.3. All right, so let's go ahead and start solving this. My first step is to get rid of those squares, those exponents. So 0.81 squared is equal to, I have 0.6561 divided by 1.5 squared, which is 2.25 times X is equal to 15.3. Okay, so whenever I'm solving this, I want to get X by itself. The first thing I want to do is move X from the denominator up into our numerator. So I do that by multiplying both sides by the reciprocal. So times 2.25 X cancels out here, times 2.25 X. Okay, so let's go ahead and rewrite this. So I have 0.6561 is equal to 15.3 times 0. Oops. Oh, what? I don't want to erase that. I want to erase down here. Okay, the eraser is being a little wonky. Okay, 15 times 15.3 times. I wish there was just like a backspace. Is there? This is so hard to do. For whatever reason, when I cover the actual stuff I want to erase, it is erasing on top. So, little technical difficulties, so just bear with my ugly handwriting. I'll just scratch that out. I'll just scratch that out, guys. That's easier than erasing. Sorry. Okay, so let's try this again. 0.6561 is equal to 15.3 times 2.25x. Okay, so we need to distribute that 15.3. So 15.3 times 2.25x is going to give us a relatively larger number. 15.3 times 2.25 is 34.425. So I have 0.6561 is equal to 34.425 x. So I'll put 34.43. Okay, so it is being multiplied by that x, and I don't want that x to be multiplied by that anymore. So I'm going to divide both sides by that value. Okay, so it's 34.43, 34.43. 0.6561 divided by 34.43. Okay, and I get x is equal to 0.019. Okay, so that M is equal to the concentration of O2. So I do apologize for the slightly messy calculations here, but this is your final answer. Okay. So if you need me to go over any more of these example students, I suggest you come to the live session tomorrow, and I can explain anything that you don't understand from today. Okay, let us continue so I don't spend too much time because I am running out of battery on my iPad. Okay. Okay. However, what if the concentrations that we are given are not the concentration at equilibrium? What do we do then? So that is where we need to do the wonderful ICE tables. You students might be a little too young to know who this gentleman is, but that's Vanilla Ice from the iconic video, which I'm not going to sing that song, but you might recognize it if you see that. Okay, so let's go ahead and get straight to it. So ICE tables. So what is an ICE table? ICE, I stands for your initial concentration. C stands for your change in concentration, and E is your equilibrium concentration. Okay, these are set up looking like this. So sometimes I like to add just one extra variable. So instead of ICE tables, if I add an R, they become rice tables because we love our rice. Okay, so we have our reaction and then our initial change in equilibrium concentrations. Okay, so this looks good here, but now let's put it into practice. Okay, ICE tables are only used if you need to calculate a new concentration. Allow X to represent the change as the reaction reaches equilibrium, and always plug concentrations measured in molarity into the ICE table. Okay, so this is our example, and you have one very similar to this in your assignments. So it says the equilibrium constant for the conversion of cis-stilbene to trans-stilbene is 24 at 200 degrees Celsius. So we are already given, so we are already given our equilibrium constant, which is 24. Suppose that initially only cis-stilbene is present at a concentration of 0.85 molar. Calculate the equilibrium concentration of cis and trans stilbenes. Okay, so we have our structure for these two organic compounds. So don't worry too much about the names or anything like that. They sound funky to you because we haven't gone over cis and trans. Just notice the orientation of some of the functional groups, some of these extra groups here on the side. Okay, so let's go ahead and start filling out our ICE or rice table. So our initial concentration, we already have our initial concentration given to us, which is 0.850 molar. Okay, so that is our starting concentration for our reactant. And at the start of this reaction, we are not going to have any of our product, so our product concentration is going to be 0. Okay, our change, I don't know how much my concentration is going to be changing, so I am just going to represent it with the variable x. So my change of my reactant concentration, I know that some of this is going to decrease as it is converted to a product. So it is going to be minus x, and then our product is going to have some added to it. So this is going to be plus x. So that means at our, At our equilibrium, this is 0.850 minus x, and this is just x. Okay, so now let's go ahead and solve this. So our first step is to write our equilibrium expression. Okay, so equilibrium expression, Kc is equal to product over reactant. So I have the concentration of trans stilbene over the concentration of cis stilbene. Okay, there is no coefficient or anything here, so that is it for our equilibrium expression, Kc. So now let's go ahead and fill this in. So at equilibrium, right, which is here, so at equilibrium, my trans stilbene concentration is just x divided by my equilibrium concentration of cis stilbene, which is 0. This thing moves. Go away, please. Go away. There we go. 0.850 minus x. And all of that equals my equilibrium constant of 24. So I need to rearrange and solve this for x. I do not need to use a quadratic equation, quadratic formula for this, but it does require a little bit more algebra. Okay, so my first step is to get rid of whatever is in my denominator. Right now I have 0.850 minus x, so I'm going to move that to the other side by multiplying both sides by the reciprocal. So multiplying both sides by 0.850 minus x cancels that out here, times 0.850 minus x there. Okay, so now my next step is to do some distribution. Okay, so this 24, I'm going to distribute to these two values there. Okay, so when I rewrite it, I'm going to have, x is equal to, so 24 times 0.850 is 20.4. Oops. Oh, I already had that written down. Okay, go back. So x is equal to 20.4 minus 24x, right? Because 24 times x is just 24x. Okay, so let's get this so that all the x's are on one side. So I will add plus 24x here to both sides. Okay, so x plus 24x, I have 25x is equal to 20.4. Okay, to get x by itself, right now it's being multiplied by 25. I want to do the opposite to get x by itself, so divide both sides by 25. So x is equal to 20.4 divided by 25. So x is equal to 0.816. So one way you can check your work is the x value that you calculate cannot be larger than your starting calculation, because once you plug it in, you cannot end up with a negative concentration. So since I do have 0.816, that is less than 0.850, that means I am on the right track. Okay, so now let's go ahead and come up with our equilibrium concentrations. So the concentration of cis stilbene, I'm just going to put cis for short, is equal to 0.850 minus x. So 0.850 minus 0.816, 0.850 minus 0.816 is equal to 0.034. And then the concentration of trans stilbene is just equal to x, which is equal to 0.816, and these are measured in units of m molarity. So that is it. That will be my final answer. My cis configuration, concentration, and equilibrium, 0.034. My trans is 0.816. So you can see that these concentrations are not equal. However, that means they are fixed. That means my cis concentration will maintain 0.034. Trans will stay at 0.816 as they are being converted from one back to the other. Okay? And so then let's see. If I have, I'm going to try something here. If I have a K value of 24, so I'll just do this here. I'll do it a separate color so we don't get too confused. 24 is greater than 1, right? So that means the products are favored. And we do see that because we have a greater concentration of my product, which is trans, than my reactant, which is the cis configuration. Okay, so remember to your K value here, and it's either going to be greater than or less than 1. This one is greater than 1, so my products are preferred, and you do see that again in the concentration differences, excuse me. Okay. So let us continue before this video becomes any longer. So I just had the Kc value there. Oh, I thought I took out the... Okay. So this one, I am not going to solve this one with you guys because this example requires the quadratic formula. I will post a separate video of myself solving a couple of these quadratic formula examples. However, I mentioned in my other video when I was solving the problems, excuse me, that I do not think that they are going to be asking you to solve one using the quadratic formula on this year's AP exam. Maybe on previous years they would, but on this year's exam, since it is only 45 minutes, highly doubtful they are going to request calculations of this degree. Okay, but let's go ahead and just read through the problem and fill it in. So it says, for the reaction of H2 gas plus I2 gas to yield 2 moles of HI gas at a certain temperature, the value of K is 56. If the initial concentration of H2 is 0.0175 molar and of I2 is also 0.0175 molar, what will be the equilibrium concentration of each reactant and product? Okay, so my initial is what is given to me, 0.0175, and the initial concentration of my product is 0 at the start of this reaction. So my reactants are decreasing by some value x, and my product is increasing by some value 2x. So this 2 comes from the coefficient 2. Okay. Okay, sorry. So when I rewrite it, it's 0.0175 minus x times 0.105 minus x, and then 2x. So starting with the Kc value, it looks like this, right? So we fill it in, it looks like this. And when you solve it using the quadratic equation, you should get a value of x of 0.0138. So I will solve this again in a separate video. I will try to have it up tomorrow. So you can watch that if you are interested in how those are solved. But I am not going to give you any further practice using that, using the quadratic formula, not for this year's AP exam. Okay, and that'll be it for this video, my students. So this is the lecture portion of the video. I already have the other video recorded where I'm solving the calculation, so I will upload both of those to your Google Classroom. Okay, if you have any questions, comments, or concerns, please email me, contact me. Either, again, my email m.valdez10@ljisd.com, or you can submit a private comment anywhere in Google Classroom, and I will be sure to find it. Okay, That is it, students. So have a wonderful rest of the evening. Take care. And